Welcome to the solutions test review. So let's spend a minute talking about vocabulary. There are less than 6 math problems on this test, and so you are going to need to study the definitions very thoroughly. We had you do the list for Parker Points. If you didn't do that list, then I highly suggest at the bare minimum you do the definitions that we have listed on the review. I suggest you do all of them, but at the bare minimum do the ones that are listed on the review. The first section of this review is about the properties of water. Some of the things that we did in Water Olympics, wants to know what the properties are. We know that water has a high boiling point, has a relatively low freezing point. We talked about cohesion and adhesion. Remember, cohesion is where the water particles want to stick together with each other. That's why we get things like water droplets, and then adhesion is when water wants to stick to something. For instance, when water beads on the car, it sticks to the car. It doesn't just roll off because it has an attraction for it. We need to know that ice floats because it is less dense than its liquid form. It has a high molar enthalpy of fusion, high surface tension. I didn't list it here, but it also has a high specific heat, meaning it takes a long time for it to heat up, but it also takes a long time for it to cool down. That's why our waterways don't get very, very hot or very, very cold when the temperature outside is really hot or really cold. The next question says, what leads to the high boiling point of water, the surface tension, and the open framework present in ice that makes it less dense? All of those properties can be explained by hydrogen bonding. Remember, hydrogen bonding is whenever we have a polar molecule and we have one side that's slightly positive and one side that's slightly negative. And then, of course, hydrogen bonding is with highly electronegative things. And in the notes, we drew a picture, so make sure you refer back to that, where we drew a picture of the oxygen having lone pairs of electrons, and the hydrogen on the nearby molecule is attracted to that, and it forms those hydrogen bonds. And remember, hydrogen bonds are the strongest of the intermolecular forces. And then the last one wants to know why is water the universal solvent? And it is because water is polar. Remember, this is what we drew it like, hydrogen, and we have our oxygen with our 2 lone pairs of electrons. And because of that, this side is slightly negative, this side is slightly positive, and so that's why it is a polar molecule. And so because of that, it can dissolve other polar items and then also ionic ions. And so because of that, it dissolves a lot of things. It's hard to actually keep good pure water because it is such a good solvent that things like to dissolve in it. Types of mixture is the next section on your review, and again, this is when those definitions are going to come in handy. It wants to know what is a mixture of metals, and the solution of metals we call an alloy. And we talked about examples of brass and bronze being alloys. Remember, those are homogeneous mixtures. Remember, homogeneous means the same throughout, uniform in composition. You can't tell the difference. And then, of course, heterogeneous, we talked about how that was different in composition or not a uniform composition. Things like chicken noodle soup, sand would be an example of a heterogeneous mixture, or granite would be an example of a solid heterogeneous mixture. Then it wants to know within mixtures, explain how you would be able to tell the difference between a solution and a colloid, and what is this called. And we talked about it in class, where if you shine a beam of light through a solution, it does not scatter light, meaning you can't see it pass through. But if it's a colloid, it does scatter the light, and you can see the beam traveling through the colloid. And we talked about fog, the difference between driving on a clear night when you couldn't see the beams of the car, and then on a foggy night, if you turn the beams on, you could actually see the beam of light traveling through the fog because fog is a colloid. And that is called the Tyndall effect, and I've underlined that because that's another one of the definitions you're required to know. And the Tyndall effect, again, is the scattering of light by colloid particles. All right, so we had this table to fill in concerning the differences between solution, colloids, and suspension. And so the type of mixture for a solution is homogeneous. It has a small particle size, and it cannot be separated by filtration. And remember, when we're talking about solution, the solute is what's being dissolved, and the solvent is what's doing the dissolving. A colloid is a heterogeneous mixture. Their particles are intermediate in size, and they can't be filtered out. And then the last one, suspension, is heterogeneous. It has very large particles, and it can be filtered out. And remember, a suspension the particles will settle out if it's not continuously stirred or agitated. And then I have this little side note right here concerning the particles of colloids. And I just want to make sure we talked about solute and solvent, but with colloids it's a little bit different. We call the colloidal particles. They form the actual dispersed phase, and that's what's being dispersed throughout the colloid. So in the case of fog, the water molecules that we see would be the dispersed phase in the air, and then the dispersing medium, which is solvent-like, would be the air itself. So I wanted to make sure you understand that the colloidal particles form the dispersed phase, and the dispersing medium is like a solvent when we're similar when we're talking about solutions. All right, the solution process. What 3 ways can you increase the rate of dissolving a solute? In class, we talked about heat it, crush it, stir it. The whole goal to increase the rate is to increase the amount of solute and solvent particles that are interacting with each other. The more interactions, the faster it will dissolve. By heating it, of course, anytime we heat anything up, the temperature, the speed of the particles increase, and so as the speed of the particles increase in the solvent, that means they're going to be moving around faster, so more interactions. Crushing it is about the surface area. The smaller the surface area, or the more surface area, I guess, by having smaller particles, I guess is a better way to say that, means it would dissolve quicker. In class, we use the example of if you're putting some sugar in your tea, granulated sugar, which we usually have in our sugar bowls, will dissolve much quicker than the old sugar cubes that our grandmas like to use or that we like to feed the horses, because the solute has to dissolve layer by layer. And then the last way was stirring it or agitating it. And by stirring it, of course, we're increasing the speed of the particles by moving it around manually ourselves. But if we didn't stir it and we just put the sugar in there without stirring it, what would happen is the layer between where the solute and the solvent were interacting, the solute particles would build up really concentrated right there, and then it would be harder for some more solute to be dissolved because you would be concentrated right there at that little layer. And so that's why we have to stir it so we can put fresh solvent particles in contact with our solute particles. The next thing says explain the difference between saturated, unsaturated, and supersaturated solutions. Remember when we're talking about these and we were talking about our solubility curves, it's always per 100 grams of solvent. So if we were talking about water, this would be how much could dissolve in 100 grams of water. Saturated contains the maximum amount at that temperature. Remember, they are temperature dependent. So at the maximum amount, you're saturated, meaning you can't put any more. And we talked about that when you pour sugar in your tea and you stir, and after you finish stirring, you get a layer of sugar in the bottom because no more sugar will dissolve. So that would be a saturated solution. Unsaturated is when it contains less than the maximum, meaning we could still put some more sugar in there. And then, of course, supersaturated contains more than the maximum amount. And supersaturated are the most unstable, and they're the ones that tend to, if we were to disturb them, would crystallize, or if we dropped a seed crystal in there, they would crystallize as well. And we talked about that's how you make rock candy. You heat it up, dissolve way more sugar than it can normally contain, and then you cool it back down, and that sugar will crystallize out. All right, so for the test, you need to be able to read the solubility curve, which we did a worksheet over. And so here is the solubility curve that we're going to be looking at. And let's just answer these 2 questions about it to make sure we understand how to read it. Remember, it's always per 100 grams of water that we're dissolving it. And so if I wanted to know how many grams of potassium nitrate will dissolve at 60 degrees, then I would go over here and find potassium nitrate. And of course, remember that's KNO3. And I would find potassium nitrate, and I would find 60 degrees, and I would come up here and I would follow 60 degrees until I got to potassium nitrate, and I would see that it is 110 grams of potassium nitrate would dissolve in 100 grams of water. The next question is asking at 70 degrees, if 40 grams of potassium chloride were dissolved, what type of solution would that be? So I'm going to come over here to say 70 degrees right here, and I'm going to see where 40 grams lands, and it's right there. And of course the line for potassium chloride is up here, and so since I am below the line, I would have an unsaturated solution. And remember, if it is on the line, directly on the line, then that is considered to be saturated. So anywhere of these line at those temperatures is saturated. If it's below the line, it's unsaturated. And of course, if it's ever above the line, then it's supersaturated. So an example of that would be, let's go back to that KCl. And if I had dissolved that 40 grams at 70 degrees, which is right here, but then I cooled down that potassium chloride to the freezing point, I would be above that KCl line. So now my solution would be supersaturated and it would be very unstable. Explain what like dissolves like means. When we're referring to like dissolved like, we are referring to the polarity of the molecule. If something is polar, it's going to dissolve other polar things and also ionic, and we talked about that a little earlier. That's why water is such a good solvent, because it's polar. So not only will it dissolve other polar molecules, but it will also dissolve ionic. And the reason that they go together is because, remember, polar has a slightly positive and a slightly negative end, and so they're attracted to not only other molecules that way, but they're attracted to ionic compounds. Because remember, when ionic compounds dissolve in water, they ionize or dissociate and break apart, and so then you've got positive and negatives being attracted. And then nonpolar doesn't have a charge, a slightly positive or a slightly negative, and so it will only dissolve other nonpolar things. And so that's the reason that, say, oil and water don't mix, because water is polar and oil is nonpolar, so they do not mix. All right, so what is molarity? It is moles of solute over liters of solution. We oftentimes will abbreviate it mole over L for moles over liter. Now we're getting to the problem part of our review, so I want you to pause the video and you work the problems and then restart the video to see if you worked it correctly. All right, so how'd you do? Remember, when you're doing these kind of problems, when you're solving for grams, if you'll remember that volume in liters times molarity is equal to number of moles, and then once you get to that point, you can multiply by the molar mass. So I took 1 liter, I multiplied it by the molarity, which was 3.50 moles per liter. Of course, the liters cancel out here and here, and I was left with 3.5 moles of H2SO4. And so then I take that moles and I multiply by the molar mass of H2SO4, which is 98.09. And then when I do that, of course, my moles are canceled out, and I'm left with 343.315. But of course, I need 3 significant figures, because that has 3 and that has 3. And so my final answer would be 343 grams of H2SO4. Again, make sure you pause the video and work this problem yourself. Please don't just watch me work the problem. You need to try to work it yourself to make sure that you understand how to work it. This really should just be a way to check yourself. All right, so here's the answer to this one. So how did you do on this one? A couple of things to make note of. Make sure that you change milliliters to liters. We do that by dividing by 1,000, because remember, there's 1,000 milliliters in 1 liter. And then we do, again, volume times molarity gives you number of moles, and that's all it's asking for in this problem. This problem is asking, what is the molarity of a solution if I dissolve 26.42 grams of the ammonium sulfate in enough water to make 50 milliliters. Remember, these little numbers these numbers are supposed to be little in these. It's just that for some reason this program won't do that. So pause the video and work the problem, and then come back and see if you got it correct. All right, so you should have gotten 4.00 molar ammonium sulfate solution. And the reason it's 4.00 is because if we look back up here, it is, actually it needs another 0. I didn't catch that. Actually, it needs to be 4.000 because it needs 4 significant figures. So the way we did this, in case you got this wrong, is we took the amount that we dissolved that they gave us in the problem, we divided by the molar mass because we needed to convert grams to moles, then we got number of moles, and then in order to do our molarity, because remember molarity is moles over liter, we took those moles and divided by the volume in liters. And up here we went ahead and changed that up here and divided by 1,000 to get 0.05 liters, and then that gave us our answer. All right, this is the last one of the workout problems that we need to do. It wants to know how many milliliters of a stock solution of 12 molar HCl do you need to prepare 1 liter of a 3.5 molar solution. And whenever you see something with 2 molarities in 1 volume, that is your clue that it's going to be the dilution formula. So pause the video and work this and see what answer you get. Okay, you should have gotten 290 milliliters with the correct number of significant figures. So we're using that M1, V1, and of course we rearrange it to solve for V1. Just a quick note, remember that M1 is always going to be your higher molarity because it is the concentrated, and M2 is your dilute, so it's always going to be the smaller. But you've got to read your clues in the problem to know what you're going to be looking for. This one specifically said how many milliliters of the stock solution, meaning the concentrated, so that's going to be V1. After we solved for that, we actually got 0.291 liters, but this one asks for it right here in how many milliliters. So we need to be mindful of that when we're reading these problems. And so of course we take that liters, use the conversion factor of 1,000 milliliters to 1 liter, and we get 291 milliliters. Because of this right here, we require 2 significant figures, and so that answer would actually be 290 milliliters. Okay, last 2 questions on the review. List and explain 3 colligative properties. Here we have boiling point elevation. Remember that means it's going to increase the boiling point of a solute, of a solvent. We have freezing point depression, which means we will lower the freezing point. And then also vapor pressure depression, which means we lower the vapor pressure. The last one is talking about if you had 1 mole, so you have an equal concentration of all these things added to water, which one would have the highest boiling point? And so we wanted to know which one would affect that boiling point elevation the most. And remember, it's the number of particles that does that. So again, this is supposed to be little subscripts. So H2SO4 would have 3 particles because it would go into 2 H pluses and then 1 SO4 minus, 2 minus, excuse me. And so you would have a total of 3 particles. Here we'd have 3 plus 2, we'd have 5 total particles. The HCl would have 2 particles, and the ammonium hydroxide, NH4, is polyatomic, and the OH is a polyatomic as well. So you would have 2 particles here. So what would have the greatest effect is the magnesium phosphate. That would be with the 5 particles, it would have the greatest effect. So that solution would have the highest boiling point. Okay, I want to remind you again to please study those definitions. We went over several of them. Also, you did hopefully the definitions for the Parker points. And if you did not do those, you should go back and do those, specifically the ones that were listed directly in the review. So stay tuned for jokes. If you don't want to hear the jokes, then stop the video and continue your studying. All right, this time our jokes have to do with our solutions unit. So here's the first one. Why did the white bear dissolve in water? Because he was a polar bear. What do you call 2 teeth in a glass of water? A 2 molar solution. And finally, why are chemists great at solving problems? Because they have all the solutions. All right, continue to study for your tests. Good luck tomorrow.